Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. For the quint post shown below, the beam is rectangular in cross-section measuring 200 mm by 300 mm with modulus of elasticity 12 gigapascals. The vertical struts are 75 by 75 mm with the same modulus of elasticity as that of the beam. The steel bars, E 200 gigapascals, are circular, 10 millimeters in diameter. Determine the forces in each strut, the bars, and the maximum bending moment in the beam. Neglect shear effects in the beam. So here is our last example. This is a quint post. So let's select the force in member EF as our redundant. We'll call that Q. Then summation forces X to solve for these two members in terms of Q. So 1.25 Q. This is also 1.25 Q. The slope of this member, by the way, these two, is 3 vertical, 4 horizontal, then 5 hypotenuse. The length is 2.5. 2 divided by 0.5 is 4. Then 1.5 divided by 0.5 is 3. So that's why 3 vertical, 4 horizontal, 5 hypotenuse. So you can derive this. And summation forces vertical, the force in CE is negative 0.75 of Q. This is also negative 0.75 of Q. So compression. Then the effect of this 1.25 Q to the beam is to compress the 6-meter length beam. So by summation forces vertical, this is 1.2 times 6 divided by 2, then minus the vertical component of 1.25 Q. That's why you have here negative 0.75 of Q. Same is true at D by symmetry. Then the force in AD is Q, and it compresses, that's negative, it compresses beam AD. For our sectioning, X, same is true here. So we just double. And for the middle segment, it's different. So let's have another sectioning. So partial of U with respect to Q equals 0 equals 2 times integral from 0 to 2 for this segment and this segment here. The moment about this section is quantity 3.6 minus 0.75 Q times X minus the moment of the load, which is 0.6 X squared or 1.2 times X over 2. And partial derivative with respect to Q is equal to negative 0.75 X dx over E of beam, I of beam. Then in this section here, plus quantity, integral quantity 0 to 2, 3.6, quantity 3.6 minus 0.75 Q times 2 plus X minus 0.6 plus, rather we have compressive force here of 0.75 Q times X, then minus the moment of this load, 1.2 times quantity 2 plus X over 2, so that's 0.6, 2 plus X squared. And partial derivative with respect to Q is negative 0.75 2 plus X plus 0.75 X dx. If we simplify this, this is simply negative 0.75 times 2 or negative 1.5. Then for the axial forces, let's begin with Q times 1, the length is 2 over area of rod, E of rod. Then for these two combined, or times 2, 1.25 cube derivative 1.25, the length is 2.5 over area of rod, E of rod. Then for these two struts, 2 times negative 0.75 Q, negative 0.75, the length is 1.5 over area of strut E of bar, or E of strut, E of beam rather. Then finally for the beam, plus Q, negative Q times negative 1, length is 6 over area of bar, area of beam, E of beam, and equals 0. Simplifying, the first is 3Q minus 10.8 over E of beam, I of beam. This one, 4.5Q minus 15.6 over E of beam, I of beam. Then we have 125Q over 16 over area of rad E. By the way, just verify, or maybe these two are combined because they are like terms. This is just 2Q over area of rad E. Then this one, 27Q over 16 over area of steel rad E of beam, area of strut, not E of beam. Then they are combined. This is just 6. So simplifying, we multiply this by 1000. We combine the two, and multiply 1000 to the fourth over E of beam, 12,000 megapascals moment of inertia, 200 times 300 cube over 12. Then for this, 157Q over 16, so that's 2Q plus 125Q over 16. These two are combined. 1000 square over area of rad pi 5 square, then E of rad 200,000 megapascals. Then for this alone, 27Q over 16 times 1000 square over area of strut is 75 square, then E of beam 12,000 megapascals, then plus 6Q over times 1000 square over area of beam, which is 200 by 300, then E of beam 12,000 equals 0. So simplifying, combining for this term, the result is 25 over 18, and for this one is 0.62468. Then this one is 1 over 40, and this last is 1 over 120. Then the constant is only 26.4 times 1000 to the fourth times 12 over quantity 12,000 times 100 times 300 cube, and that is equal to 44 over 9. We can now solve for Q. Q is 2.3884 kilonewtons, and from there we can compute the forces in the struts, the bars, and the maximum bending moment. So this is the stress in EF, tension 2.388 kilonewtons. Then for AF, 1.25 of Q, so 2.985 kilonewtons, equal to stress in DE also. And for the two struts, SBF, SCE, because this is negative 0.75 of Q, negative 0.75 of 2.3884, negative 1.791. Then for the beam is just Q negative, it is also compression. So it's not as, therefore the maximum moment occurs at the center. You evaluate also at B. So this is the moment at B. quantity 3.6 minus 0.75 of Q times 2 minus 1.2 times 2 times 1. So moment at B is 1.218 kilonewton meter, whereas the moment at center is quantity 3.6 minus 0.75 of Q times 3 plus 1.791. Remember, this is 1.791 compression times 1, then minus the moment of the load, 1.2 times 3 times 1.5. So moment at center is 1.818 kilonewton meter, which is greater than that at moment at B. Therefore, the maximum moment is 1.818 kilonewton meter. So that's it for this problem.